Hi, my name is Scott Simpson, and today we'll be talking about electron configurations. Now, in Gen Chem, you often have to list the orbital occupation of an atom. So what's a common example of this? So let's say we have something along the lines of carbon. So carbon would have a configuration, we often write it like this, would have a configuration of the 1s, 2, 2s2, 2p2. Now, what we have here is we have our shell number, what type of orbital we're looking at, and the occupancy of the orbital. So this right here is our shell number. This is related to the quantum number n if you look at a previous tutorial. This right here, this s, is the type of orbital we're looking at. This is related to the quantum number L. And then this number up here is the occupancy of the orbitals. So what I mean by occupancy, how many electrons are accommodated in that type of orbital. Now you may see a diagram that is similar to this, where you would have the 1s down here, then the 2s, then the 2p. Now let's talk about this for a little bit. I'm going to erase this stuff up top. And what this is called is an electron configuration diagram. Now, the way you're meant to draw these is with Hund's rule and the Pauli exclusion principle in mind. So the Pauli exclusion principle says we can't have two electrons with the same spin occupying the same quantum state. So when we look at an energy level, we must have an electron pointing down or up and one pointing down. If they're both pointed the same way, this violates the Pauli exclusion principle, and we can't do this. Next is Hund's rule, where Hund's rule states that you must fill the electrons starting with the lowest energy and then moving to the highest energy. Now, we also must consider how many electrons carbon has. So since this is carbon, carbon has 6 electrons total. We knew that from our electron configuration, which I just erased, but also if you count on the periodic table, you'd notice that carbon has an atomic number of 6, so it matches. So we have to start filling our electrons. I already filled the 1s for us, but let's move up to the 2s now. Alright, and now we're to the 2p. And if you notice, these are our core shells, or valence shells, which I'm actually going to mark off in green. And these are typically the ones that do all the bonding. Now, another thing that is very important to note is the energy of each of the shells. So notice how the 1s is the lowest in energy, and then as we move to the 2s, it's a little bit higher in energy, and the 2p is even higher in energy. So there's kind of an energy ordering where so we'll go from lowest energy to highest energy. So if we move through our orbitals, S would be the lowest in energy, followed by P, followed by D, followed by F. And we can go further than that, but in most cases you really don't worry about that. Now, what about a condensed electron configuration? What about something like sulfur? Well, sulfur you could write in a few different ways. So you could write the full electron configuration of sulfur in such a fashion. P 6 Then we, oh, I'm sorry, that should be a 2p. Then we would move to the third subshell, S, then 3p4. We could write it something like that. But there's an interesting thing you can do. Instead of writing this full electron configuration this way, you can just state, all right, we know it's going to have the same inner electrons as a noble gas that's on the periodic table. And if we look at our periodic table, which I don't know, let's see if that's good enough. If we look, the closest to sulfur would happen to be this neon. You don't actually go this way, you go to the lower atomic number. In this case, it would be neon. So we could also express sulfur as the same electron configuration as neon, and then just include the valence orbitals. So it'd be the 3s2, oops, oh, I wrote a p, and then 3p4. So the other important point is we have to know about the d orbitals, right? So p orbitals have 3 degenerate states, and what I mean by degenerate is they have the same energy. The d states have 5 orbitals that are degenerate. So 5 orbitals that are the same energy. So let's look at something simple. Let's look at, let's look at titanium. That seems like a good one. All right, so titanium. It would follow something along the lines of this. So titanium. Let's look at the atomic number of titanium. So titanium should have how many electrons? If we look, titanium should have 22 electrons. So 22 electrons. And what I'm going to do is go with the condensed structure. So we look for titanium's closest noble gas, and it's argon. All right. So this would be the same thing as argon. And what shell number does it start with? Well, that one's kind of easy to do. All you have to do is look, okay, 1, 2, 3, 4. So we start with shell number valence 4. So 4s2. Now here's where it gets kind of tricky. Since we're dealing with the transition metals, what ends up happening is there's a D state that's located in here. And the D states are actually in the n equals 3 shell number. So you have to include the 3 D states. So the interesting thing is some people like to write this way, and others like to write it this way. And the difference between these two is subtle. It kind of depends on how your grader is going to grade this. Technically, this one is with respect to the energy because the 4s is lower in energy than the 3d. And in this case, it's going by quantum shell number. So we start with 3 and we move to 4. Let's draw an electron configuration diagram, and you can decide which way you like better for titanium. So what I'm going to do is I'm just going to ignore the valence shells. Or I mean the core shells, so the ones that are not the valence shells. So we're only concerned with the 4s2 and the 3d2. So This is our 4s2, and then we'll occupy it with 2 electrons. And then here is our 3d. Now I said that the 3d is lower, or is higher in energy than our 4s, which is true. Even though the 3d has a smaller n value, or principal quantum number. So let's just fill in our electrons for the d, and notice, keeping the Pauli exclusion principle and Hund's rule in mind, that the first 2 electrons get occupied in this fashion. You don't do something along the lines of this. This follows the Pauli principle, but not Hund's rule. So we have to do something along the lines of this. All right, so looking at this, you can see that the 4s is indeed lower in energy than the 3d. But it seems weird that we place them with these different electron configurations. It all depends on if the principal quantum number is more important to you or the energy ordering is more important to you. All right, so there's a neat way you can go about trying to determine the atomic orbitals an atom will have. The periodic table is actually set up in a really, with this in mind. So if you have a periodic table next to you, you can look at it and you can determine, okay, all of these are for the S states. All of these over here are for the P states, and all the ones in the center are for the D states. So if you want to look at the valency, let's look at the valency of, let's look at aluminum. We would know that the 1, 2, 3, 3s has 2 electrons occupied in it, and then the 3p has 1 electron occupied in it. Let's say we want to look at something like vanadium, which is V right here. We would know that we were in the 1, 2, 3, 4. 4s would have 2 electrons occupying it, and then we would have to go back 1 quantum number because of the way the d orbitals fill, and we would see that the 3d would have 1, 2, 3 electrons in it. So knowing this, you can just use the periodic table to actually give your electron configuration. I hope this was helpful, and if you have any questions or I was not clear about something, please leave a comment below and I hope to help you. Thank you very much.